Since many of you likely have not seen trigonometry for a while, I figured it'd be good to just review what sines and cosines look like and where they come from. So it all comes from the unit circle, where we make different triangles. So here, I've made a triangle where this angle I've called theta. And we can relate the size of the different sides of the triangle using trigonometry. So we have a nice mnemonic to help us remember. We call that mnemonic, so katoa. And if I look at the different sides, we can see that there's one side that's opposite of my angle. There's one side that's adjacent to the angle. And since this is a right triangle, the side opposite the 90-degree angle, the longest side, is called the hypotenuse. Well, we can use sines, cosines, and tangents to relate the angle to the lengths of those sides. So from what we can say is that the sine of the angle is equal to the opposite over the hypotenuse. We can say from the ka that the cosine for ka, is equal to the adjacent over the hypotenuse. And from the tangent, the toa, we get the tangent of the angle is equal to the opposite over the adjacent side. Now, we can actually make a graph of what each of these functions look like. When I do that, let's just do sine and cosine. So this is the sine of an angle as a function of the angle. We can see the sine function starts at 0 and then moves up and traces out a curve. It traces out a periodic sinusoidal curve. I can do the same thing with my cosine function. The cosine, we would say that that's 90 degrees out of phase with the sine function, which essentially means it's shifted over ever so slightly. So that if I were to plot my cosine function, it starts high, and then goes down and then repeats its motion. It's the same graph as the sine, just shifted over by an angle theta is 90 degrees. The next type of motion we'll consider is called simple harmonic motion. The prototype example for simple harmonic motion is just a mass on a spring. Now, if I were to just hang a mass from a spring, there would be some equilibrium position that the mass would rest at. And if I were to displace that mass from equilibrium, either by pushing it down or pulling it up, what would happen is as soon as I let the mass go, it would start to oscillate up and down. So we want to describe the motion of that oscillation. We can do that graphically. So if I plot the y position, the vertical position, the height of the mass, as a function of time, I'll make this in meters, I'll make my time in seconds. What we'll see is that my mass will bounce up and down, will oscillate. So if I initially pick it up to some height, it will go down, come up, go down, and that motion will continue for a long time until friction causes it to slow down and eventually stop. Now, there are a couple of pieces to this motion that I want to talk about. One thing is I want to describe how big the motion is. So we call that the amplitude. So we say A is our amplitude. We could also talk about how long it takes for the motion to repeat itself. So this is a type of motion that we call periodic motion because it repeats every so often. There's a certain period to it. The period is just the time it takes to repeat the motion. So I'll call the period t, big T, capital T. So our period, again we just call that t. So my amplitude, since we're measuring a distance here, that will just be in meters. My period, that will be in seconds. Mathematically, we can describe this motion just by finding a function that fits the shape of that curve. Now there are a few functions that will do, but you may recall from high school mathematics that this is the shape of a sine or a cosine wave. So we're going to describe that in terms of a sine or cosine wave. And let's just write that down. If I want to know the height of my mass on the spring, we're going to write that as some amplitude times the cosine of 2 pi times time. So this is a height that will change over time. It'll be a function of time. 2 pi times the time divided by the period, which is how much time it takes to repeat a cycle. So we'll use this equation to describe our simple harmonic motion. Again, A is the amplitude of the motion, big T is the period, little t is the time that I happen to be looking at. Rather than talk about the period, some physicists prefer to talk about how frequently the mass goes up and down. So for this reason, we define a quantity called the frequency. Call the frequency, we give it the symbol f. It's defined as 1 over the period. So for example, suppose my spring went up and down once every half a second. So in half a second, it completes 1 cycle. Well, then my frequency would be 1 divided by half a second. Or equivalently, that would mean that it goes up and down twice every second. Now, I could rewrite my equation of motion in terms of that frequency. We could say that this is y equals a cosine 2 pi times the frequency times the time. That's equivalent. I'm just replacing the 1 over t with the frequency. However, some physicists are even lazier than that. So they've defined this other quantity called the angular frequency. And the angular frequency is sort of a nickname for this part of the equation. Essentially what we do is we absorb the 2 pi into the frequency. We give it a new name. It looks like a W, but it's actually the Greek letter omega. Give it a new symbol. Call it the angular frequency. And this is equal to 2 pi times the frequency, or equivalently, 2 pi over the period. So that I can rewrite my equation of motion as y equals a cosine omega times t. So there are several ways to rewrite my equation of motion, depending on whether I want to use period, frequency, or angular frequency. Now, a note about both frequency and angular frequency. You'll notice that we have, to get the frequency, we divide by the period, which is in seconds. So the units of frequency could be written as 1 over seconds. But usually you don't say that. Usually what you say is that the frequency is in hertz after a physicist named Heinrich Hertz, who did some work with frequency. So the units, it is correct to say either 1 over seconds or the frequency is in hertz.